Okay, hello everyone. We are back into our chapter 6 and our chapter 11 discussion, and this is kind of where we start integrating these ideas that we covered in chapter 6 about phase changes, as well with some of these ideas that we covered earlier in chapter 11 about intermolecular forces, and we can put the energies and the intermolecular forces ideas together to figure out some of these patterns and understand vapor pressure and phase changes a bit more. So let's get started. Okay, so vapor pressure is the pressure that occurs when these molecules are in a closed container and they go spontaneously from the liquid state to the gas state. And the molecules that are in the gas state bounce around and hit the walls of the container, creating a pressure above the liquid. The rate of vaporization increases with increasing temperature. So if we add heat, my fires are really bad. If we add heat to the bottom of this liquid, the molecules within the liquid are going to start moving faster because they have more kinetic energy. That's what the heat gives us, which means that more of these molecules that are on the surface are going to escape out into the gas phase. As we get more molecules in the gas phase, the pressure is going to increase. We also know that the rate of vaporization increases with increasing surface area. So this is thinking about if we make our container a lot bigger and we have our liquid, and let's imagine that this is the same amount of liquid, that now we have a larger number of molecules on the surface, and so there are more chances for these molecules to escape into the gas phase, thus increasing the pressure. And the rate of vaporization is that rate at which these molecules can escape into the gas phase. The other thing we know is that the rate of vaporization increases with decreasing strength of intermolecular forces. So, if we have water, those water molecules have they have hydrogen bonding. And so they have a lot stronger forces holding them together. And so if this is the view at the surface, it's going to take a lot more energy for this water molecule to escape out into the gas phase because he's being attracted by these other water molecules. And even more importantly, he's being attracted by water molecules that are down below the surface. Meanwhile, if we have, let's do methane, where the only thing holding this methane to another methane are London dispersion forces. Those are not very strong, which means that it's not going to take much energy to get one of these methane molecules to escape out into the gas phase. And so the weaker the intermolecular forces, the higher the rate of vaporization. So the other thing to know is that to vaporize a substance, to go from liquid to a gas, energy must be added. It's an endothermic process, and the amount of energy is given by this enthalpy of vaporization term. And so the experiment that happens with Clausius-Clapeyron, which is the relationship that we are working our way towards, is that we take a sealed container and we put a thermometer down inside of this container, and we measure the pressure within this of the vapor pressure, and we have a heat source so we can change the temperature. And so what we're doing is we're increasing the temperature of the liquid within a sealed container while measuring the temperature and the vapor pressure. Okay? And when we run this experiment, we get out a set of data that is not linear. We have vapor pressure on the y-axis, we graph temperature on the x-axis, and we get this exponential style curve that is the relationship between the temperature of the solution and its vapor pressure. These nonlinear graphs are really difficult for calculations and predictions and using the relationship. And just to prove to you that my made-up data and the relationships that I went over are actually real, here's some actual data. So if we look, ethylene glycol is way down here. We have water, we have ethanol, and we have diethyl ether. So from this relationship, you should be able to see that these molecules have increasing intermolecular forces. That ethylene glycol has higher intermolecular forces than water. And so as we add heat, there's a lot less vaporization happening. Water is a much slower rise as we add heat than ethanol. Ethanol has less strength of intermolecular forces than water does. Okay, so what is this relationship? Well, if we say that the vapor pressure is P vape, the temperature is T, we see that our pressure of our vaporization is equal to some function with respect to T. And so, yes, this is the function sign, just like you see in math class. And this is a very generic way of saying that the vapor pressure is a function of temperature. So it's related to temperature in some way. We just don't know what that way is. And so the nasty relationship, this is the Clausius-Clapeyron. I think that's spelled right. Is that the pressure of vaporization is equal to some constant. This is just a constant at this point, times E raised to the enthalpy of vaporization divided by R times T, and R is our ideal gas constant. T is the temperature. Okay, so this is a very nasty relationship to work with. There's the natural number, E. There's an exponential with a fraction, and there's this undefined thing with the symbol beta. So we are not going to use this relationship. In our next video, we're going to turn this relationship into a form that we can use. But from this relationship, we can see that this vapor pressure is related to this energy required for vaporization and the temperature. And so that means that we can experimentally figure things out and use things like the pressure and the temperature, which are measurable, to find this energy required for vaporization. Okay, so stay tuned, and we're going to continue working with the Clausius-Clapeyron and show some examples of how these problems work.